Well, good morning, good afternoon. Welcome to Issues in Environmental Science. This is week 11, and today we'll be talking about water resources. I'm going to start sharing my screen here. So you should see a version of the PowerPoint there. Everybody's able to see that?
Yes, sir.
Very good, thank you. So we'll be talking, going through some basics, which probably is a review for everyone about water properties, but they bear directly on the way the hydrocycle affects our ecosystem and our societies. And there'll be a focus on drought and water management issues, both as a ecological process and challenge, and also as a scientific and political challenge. So let me start with looking at important properties of water. Again, I think this is probably a review, but let's just have these properties in mind as we go forward with this lecture. So water, of course, is the only natural substance that occurs on Earth in all three of its possible phases, both as a liquid, a gas, and as a solid. And it's also very abundant bound in water as a mineral component of many different types of rocks and minerals. Very importantly, it has a very high heat capacity, which means that it is able to retain large amounts of heat. And this heat it has high latency. In other words, once water is heated, it takes a long time to lose its heat. As anybody who's ever used a water bottle to warm up their bed at night knows, you can put hot water in a water bottle and stick it in the bottom of your bed and warm the whole bed because the high heat capacity of water. But likewise, it takes a lot of heat energy to change water's heat content. And so that's important for understanding how water affects the weather and hydrocycle. It's virtually incompressible, which is also critical in terms of how it behaves as a natural fluid. And it's a very highly reactive compound. It's the universal solvent, and it is able to dissolve most organic minerals as a function of its polar nature. The density of water is controlled by temperature, by the amount of dissolved solids present in water, and by pressure. Importantly, water has a maximum density at 4 degrees Celsius. This is a very unusual property for any compound. Most compounds have their highest density in their solid phase, but the solid phase of ice has a lower density than liquid water, with the result that ice floats. This would be a vastly different world. In fact, this would be an impossible world if ice sank to the bottom of lakes and rivers when it froze. So how do these properties of water arise? They arise from the characteristics of the water molecule. The water molecule, of course, is H2O, but the two hydrogen atoms present in a water molecule are joined at an angle to the oxygen, which gives a water molecule a positive side and a negative side. And this polarity, it's a weak polarity, but it's a polarity nonetheless, allows organic compounds to either be attracted to one side or the other of the water molecule. And it also allows water molecules to link up with each other through hydrogen bonds. And this linking is responsible for the high heat capacity of water, and for the fact that we just discussed that that water has its maximum density at 4 degrees Celsius as opposed to when it's in its frozen state. So in water is a gas. It, behaves as a gas. Let's see. And as a liquid, there are weak hydrogen bonds that join the water molecules together in long strings called ligands. And as you lower temperature in water, as you remove heat from a body of water, these bonds and the linkages between the water molecules increase over time. And when they form up all of the bonds are formed and the water becomes solid, these arrangements of these atoms have their maximum density. So they increase in water. The average angle between water molecules is 105 degrees. And when all of the bonds are present, when water is transformed from a liquid to a solid state, the bonds, the angle between water molecules, the average angle increases to 109 degrees. And so this has the effect of increasing slightly the mass of frozen water and decreasing thereby its density. So water on Earth, of course, has this property of latent heat. And so if you want to change liquid water to vapor, you have to break the hydrogen bonds between every single one of the water molecules so that the water can behave as a gas, and each molecule can behave separately from the others. Likewise, if you want to transform liquid water into solid water, you have to form bonds between all of the water molecules. And the breaking of these bonds and the formation of these bonds requires either the addition of heat energy for breaking bonds or the removal of heat energy for forming the bonds. And this gives rise to this property of latent heat. So heat is often measured in calories, and a calorie is the amount of heat required to raise the temperature of 1 gram, 1 cubic centimeter of water by 1 degree Celsius. So if you add a calorie of energy to a liquid water, 1 calorie will increase the temperature of the water by 1 degree while it's a liquid. However, if you want to change its phase, either from liquid to vapor or liquid to solid, you have to add additional heat to perform that transformation. So to break all of the hydrogen bonds between the individual water molecules takes a great deal of heat, and that heat is added to the system without changing its temperature. And this is a property which you might notice if you're boiling an egg and you bring the temperature up to a very hot temperature, and you could put a thermometer in and read that you'd be very close to 100 degrees Celsius, but the water still wouldn't be boiling. And it would have to sit on the stove for some period of time until the temperature rises enough to begin vaporizing the individual packets of water. So this latent heat of vaporization, 540 calories per gram, is then a component of the water vapor. So this water vapor has this potential, this latent heat of 540 grams per calorie, 440 calories per gram. So this latent heat then, if the water vapor then condenses back to a liquid, this heat is released. So that means that the heat can be stored in water as a vapor and then released if the vapor is then precipitates as water. And so this property means that you can transfer heat by moving water as water vapor around the planet. Okay, so this is very important for the hydrocycle. The biology of the hydrocycle, as we discussed previously, and I'm sure this is clear in everybody's mind, but this is a gigantic cycle that involves every single component of the Earth's ecosystems, including the geosphere. So if we look at some of the components of this cycle, on an annual basis, 85 centimeters of water is moved onto and off or off of every square meter of the Earth. So you think about that. So there's a flux of water amounting to 85 centimeters of water per, so that's roughly a cubic meter, or 0.85 cubic meters for every square meter on Earth. However, if we think about what comprises the surface of the Earth, remember that well over 77% of the Earth's surface consists of liquid water in the form of oceans. So typically there's a net evaporative loss from oceans, and on land there's a net precipitation gain. And all this averages out to 85 centimeters, or 0.85 cubic meters per meter. And the excess water on land flows into the ocean to replace the loss of evaporation. And this keeps the cycle constant. Now, it's constant in present time, but if we look back into geologic history, during glacial stages, when large fractions of the Earth were covered with huge, thick glaciers of ice, there was a net loss from the oceans. So the sea level would decline during ice ages, or glacial periods. When we're in interglacial stages, such as we are now, there's a net gain to oceans. And so as frozen water, glaciers which are on land, melt, and that water runs off into the ocean, the sea level rises to a corresponding degree. And we're presently in an interglacial stage. However, there are still substantial ice caps covering Greenland, covering Antarctica, and covering some of the higher mountain regions in the interior of the continents. As these ice sheets melt due to climate change, we can expect to see a resulting rise in the average sea level around the planet. And of course, this is a major concern because rising sea levels are going to have an impact on coastal areas. We've discussed this previously, but it's important to have these facts clear in mind. So that is the hydrogen cycle. So if we think about the basics of hydrology, which is the study of the movement of water, major water supply problem is typically not abundance, but having the quality and the quantity where and when it is needed. In other words, there's plenty of water on Earth, but it's not distributed in a form or in an area where we can always get what we need from it. So the characteristics that make water unique are the physical and chemical properties that I just described. And within that, another concept is the concept of residence time. How long does a packet of water remain in one component or another of the Earth's ecosystem for any given period of time? And with that information, how can we consider how the supply of water is going to meet the demands of both the natural ecosystem and of human society? So water conservation and water management are critical functions of the study of hydrology. And there are environmental impacts of water projects such as dams, canals, channelization, and we'll see when we get to the end of this lecture, these water projects and water management issues can have a direct effect on local ecosystems, such as the Apalachicola Bay ecosystem, and they can become consequently very sizable legal issues. So taking the concept of residence time, because water is involved in so many components of the Earth ecosystem, there's a very broad range of residence times, depending on the phase that water is in and in what component of the Earth system the water finds itself. So starting with the most rapid or the shortest residence time, that would be in the atmosphere when water is present as a gas, water vapor. And so a typical packet of water in the atmosphere is going to be resident in that component for a matter of seconds to a matter of hours. And so, very rapidly, the water vapor is being moved by winds and and other factors. And it's also evaporating into the, water is entering into the atmosphere through evaporation and departing the atmosphere through precipitation. So this is a very, very rapid turnover. If we think about liquid water, the component of water that we're most familiar with and that's most obvious to it, this is a volatile reacting liquid. It's on lakes, streams, rivers. It's also in puddles and gutters when after the rain. And this water in this component of the system is resident for hours to months. So relatively longer, but still a relatively short residence time. And what do I mean by residence time? Just to be clear, if you take a square meter of the Earth's surface, or a column of the Earth system, starting with a square meter of the Earth's surface and going up to the top of the atmosphere, residence times means the amount of time that water is present within that column. So moving into or out of that column, either as a liquid or a gas, or as a frozen material. So if we think about most of the water on Earth is present in the ocean, the liquids in the deep ocean water masses take years or centuries to move. The relative residence time for any component of the Earth's water system in the deep ocean is going to be not measured in hours or days or months, but in years or even centuries. If we think about the water that's present in ice caps or aquifers, which we could call fossil water, that water is resident for thousands of years. And these are sort of orders of magnitude for how long the residence times last. So as glacial ice, the water, sort of the oldest ice on the planet is about 750,000 years old, and that would be ice at the bottom of the Antarctic ice sheet. The ice at the bottom of the Greenland ice sheet has a maximum age of about 350,000 years. So that gives us sort of a sense of how long the residence time for frozen water can be. In aquifers are deep components of the continental landmass, which are typically filled when there's rainwater, and also filling of the aquifers occurred on a wide scale during glacial melt period. Well, the water in aquifers is also typically present for thousands of years. Of course, human beings are impacting aquifers by pumping them for irrigation and other purposes, and they're impacting ice caps and glaciers through the indirect effect of global warming. And then finally, the longest residence time for water in the Earth system is the water molecules found within rocks. And these have residence times of millions of years. And the water that's bound in rocks is released back into the to the Earth system as liquid or gas, or eventually solid ice during volcanic eruptions. So if you get a sense of how long it takes for rocks to be subducted and then released as volcanic eruptions, you get a sense of how you can get to a million years time scale or residence time for bonded water. Okay. So what are the critical components that depend on the water cycle? Well, just about all of the critical components are present: waters, wetlands, estuaries, riparian ecosystems, rivers and lakes, urban settings, agricultural settings. These are all components of the Earth ecosystem, which are intricately involved and are shaped by the supply of water and the variability of that supply. So critical components of these systems are the precipitation and the runoff, runoff on the surface, and the movement of water, what's called groundwater, which is moving water in the upper portion of the sediments. And so this water table is has a sort of roughly equivalent to the topography of the land, but it's recharged and it flows on a relatively rapid basis. An aquifer would be much deeper than that. And so, the groundwater is typically fairly shallow. Aquifers are deeper. So these are the critical components of the ecosystem, and these are the critical ecosystems that are affected by water. You can see this diagram sort of indicating the flows, the fluxes into and out of these different systems. Well, what about the global water supplies? So generally speaking, more than 99% of the water on the planet is unusable for human consumption. In other words, 97% of it is saline water, 2% of it is frozen water. So 97% present in the oceans, 2% frozen in ice caps and mountain glaciers. The remaining 1% of water, the water that's in circulation and the water that's the most active component of this global hydrologic cycle, has a very uneven distribution. So freshwater conservation is a major issue, and 80% of the water that we use is on the surface, not underground. So, the global water supplies, and you can see here how they, how this average residence time impacts in the availability of water. So thousands of years for average residence time of any particular water parcel within the ocean. Atmosphere, average residence time 9 days, hours to seconds. Rivers and streams about 2 weeks. Groundwater, hundreds of years. And ice caps, thousands of years or longer. So this table roughly recapitulates the orders of magnitude that I described earlier. Well, if we look at the US water budget, what does that look like? So precipitation, the average precipitation, and this is, for the water resources, this is compiled for the years 1975 through 2000, so a 25-year record. There have been some changes recently, but this is, generally speaking, an accurate picture. So there's a precipitation of 152,000 million, so 152 trillion cubic meters, 152 trillion cubic meters per day, in the atmosphere moving across the surface of the continental United States. Let me explain that a little better. So if we took this outline of the United States and considered that a cubic volume, moving through that cubic volume would be this 152 trillion cubic meters per day. So that's the water motion into and out of the atmosphere over the continental US. The precipitation amounts to about 15 billion cubic meters per day. So of that 152 trillion, about 10% of it is falling as rain onto the surface of the ocean. Well, what happens to it from there? The major loss is evaporation from wet surfaces. So of that 15 billion cubic meters, about 10 billion is evaporating right away. So there's a very rapid falling and evaporation. So that's this concept that that surface water has an average short lifespan. Well, what are the other components? There's consumptive use, subsurface flow. So groundwater is moving through the loose soil and the surface of the sub-bottom or subground, and that water is flowing toward the oceans. There's also stream flow, of the water that is not evaporated, most of the water is running off as surface flows or subsurface flows. So this is a concept of the water budget. Well, this water budget, if we recall our latent heat diagram, so with this movement onto and off of the surface of the continent, moves heat into and out of the local regions. And so this has consequences for the transfer of heat within the hydrocycle. So water absorbs solar energy, but it resists changing its temperature. And this changes the way the heat is transferred around the globe. So the greatest transfer of heat is from the tropics to the high latitudes. We've discussed that. But this transfer of heat is facilitated by the movement of water vapor in the form of clouds. So water is evaporated out of the oceans near the equator or in the tropical regions. And that air with that water vapor moves with wind patterns northward or southward to higher latitudes. And in doing so, it transfers heat away from the surface, away from the low latitudes. So because the heat evaporization is very large, the atmospheric transport is extremely significant. So we can look at how that impact, with the movement of air and the precipitation are not equally distributed. It's not a sort of a uniform process. And we can see that if we look at the annual cycle of temperature in two different regions of the US. So if we compare San Francisco with Norfolk, Virginia, on an annual basis. So this is the temperature, Fahrenheit and centigrade, and this is the average temperature in each of the 12 months of the year. So if we look at San Francisco, in the winter months, San Francisco will be warmer on average than Norfolk, Virginia. And keep in mind that both of these cities are at roughly equivalent latitudes. So they're equally distant from the equator, but they're receiving water vapor and heat in very different ways because of the different wind patterns and atmospheric circulation processes to which these two cities are subject. So in the wintertime, San Francisco is generally cooler than Norfolk, although both of them, are relatively temperate. They doesn't freeze in either of these cities typically. But then as you move through the year, you can see that the temperature in San Francisco rises much more slowly. And in the hot months of the summer months of July and August, San Francisco is typically going to be much cooler than Norfolk, Virginia. Norfolk, Virginia would be up in the high, and an average temperature in the high 70s or 80s, whereas the average temperature in San Francisco would be in the mid 60s. And it sort of reminds you of the quote attributed to Mark Twain: "The coldest winter I ever spent was a summer in San Francisco." San Francisco has a cooler temperature. Okay, well, why is this? And both the southwest coast of the US is hot and dry, while the Gulf Coast and the East Coast is hot and moist. Both of these areas are adjacent to large bodies of water, and both of them experience onshore wind flow on a regular basis. But the southwest of the coast of the United States has a desert-like climate, and the Gulf Coast and the southeastern Atlantic coast of the US has ample rainfall and moisture. Well, this is a result of very different sorts of transfers. So the water temperatures, because of the Humboldt current and other processes, tend to be much colder on the Pacific coast. And so the transfer of heat and the transfer of water tends to be much more reduced, and they're hot and dry conditions. Whereas the warm water in the Gulf of Mexico. The Gulf of Mexico has typical temperatures of 25 to 30 degree range. Actually, nowadays, that's well above 30. So, you know, that's what's happening right now. We have very high temperatures in the Gulf of Mexico. And so that water is evaporated and it transfers heat and moisture into the southwest region of the US. So most of the water that falls as rain in the eastern United States is evaporated out of the Gulf of Mexico and the West Atlantic, here, Western Atlantic Ocean. So when it floods and so with the increasing temperature, the average temperature in the Gulf, we're getting increasing rainfall, and we've seen floods in the Midwest. Well, that flood water comes from the higher temperature and the greater evaporation and greater movement of water that's facilitated by the higher temperatures brought on by climate change. And so we think about sea level rise as being something that's associated with coastal regions, but warm temperatures in the Gulf and the Western Atlantic can also produce you know, excessive moisture being transferred to the Midwest. And so you can get sea level rise by air due to the increased transfer of water evaporating from the Gulf of Mexico and the Western Atlantic. And likewise, you know, we can get hot, dry conditions in San Francisco. So, you know, we're in California, and these hot, dry conditions have lately been producing very dangerous fire cycles. But it's important to note that, you know, although the conditions in California are dry, and they typically are dry in the late summer and winter, they're not at present under drought conditions. So there are sort of drought regions in the southern portion of California, and there's some drought in the northern portion. But the largest fires that burned this year, the Chico fire and the Camp fire, they were in a region that was not, that was dry and perhaps abnormally dry. It was not under conditions that would be considered a drought. So, you know, these climatic effects are producing changes in typical patterns of rainfall, and the ecosystems are adjusting as a consequence. So if we look at the trend in fire severity, California, Oregon, and Washington, you know, we're seeing major impacts and continuing increase in fire over this time. 2018 was one of the years with the most burning. 2019, they got a little bit of a respite because there was a lot of rainfall during 2019. And now in 2020, they're back in these conditions of high temperature, you know, not a drought, but still very hot. And they're getting unseasonably strong winds. And the combination of this dry heat and wind produces you know, very, very, very severe fire risk and danger. All right, well, let's talk now about water use capacities, because we talked about the availability of water as being, you know, for fresh water, for the uses that human society puts it to. There are different forms of water use. So off-stream reuse is water that's moved from its source, which typically a river or a lake, and then used for industrial cooling, for sewage treatment, for lots of things, and then returned to the source. So we can think of an industrial factory or a power plant that has cooling needs, so they use water to absorb some of their excess heat, and then that water is transferred back into the body that it came from. So that's off-stream use. Consumptive use of water is use of water that does not return to its resource source immediately. So that would be water that's used for watering agriculture, industrial consumptive uses of water, human use of water, so your drinking water, cooking water, and so forth, is not returning directly to the water source, whereas water for washing, flushing toilets, and so forth, that's water that does, it's reused water, but that usage changes the contamination state of the water, or the usability state of the water. So if water has been used for cooling, for cleaning, for sewage treatment, etc., the water that is returned may not be fit for other purposes. And then there's also the in-stream use of water. So water is in its natural state in a river or in a lake, can be used for entertainment, for navigation, for hydroelectric power generation, agriculture, recreation, and so forth. Well, the fact that you have these many different forms typically produces use conflicts, and we'll be talking about that as we proceed with this lecture. Well, one of the places where we see these urbanization conflicts most keenly are in how water is managed in urban environments. So urban settings are very often, cities are very often situated next to bodies of water, either coastal regions or lakes or rivers, because human society needs a supply of water, and also because a site near a body of water would allow for navigable transport. So in Europe, for example, many of the great cities of Europe are located on rivers. The Seine River is where Paris is located. Many of the European cities are located on large rivers, and these rivers were important historically and in the present day as means of transport. Well, when urban settings expand into natural ecosystems, there's a removal of the natural drainage system by covering over, filling in, and this increases the potential for overland flooding and also for erosion. Typically, development in cities means that the sort of natural soil cover and plant cover of the land is replaced with an impermeable cover, such as asphalt or cement. And with the presence of this asphalt or cement, the natural recharge of the groundwater that would occur when precipitation happens is deflected, and the water is moved. So instead of entering into the groundwater, water that falls in an urban environment is going to be concentrated and continue to flow on the surface and create problems of management. So one of the responses to water management is to construct dams, to build dams, and to alter drainage problems, to solve some of the problems created by urban runoff by impounding water in dams. And so what is the concept of a dam? Well, the concept of a dam is that you have a flow where water is flowing on these impermeable surfaces, and it's, instead of allowing it to flow, it's impounded in a region. And so this graph here shows the presence of a dam, very diagrammatically here, and the different components of the water are different, represent different supplies into this system. So the storage volume is retained in the dam to limit the flow past the dam to below the bank fill limits. So they try to maintain the water, dam operators are going to try to maintain the reservoir in such a way that they protect the downstream region from overflow. And so, what happens, however, when you get excess water flowing onto these systems where there's not, where the recharge into the groundwater has been impeded by impermeable cement and road beds and so forth, that creates impacts. And we can see how this works if we consider some of the flooding that's occurred in recent times. So dams can have a number of unforeseen circumstances. They can cause disease transmission. They can cause a mineralization of the soils. There can be a loss of biodiversity, fisheries, wetlands, and renewable resources, social disruption, and catastrophic failure and economic overload. And a great example of that was what occurred in Houston, Texas, after Hurricane Harvey. So Hurricane Harvey was a relatively weak hurricane. It came ashore as a Category 1 storm. But because of the steering currents in the upper atmosphere, instead of moving inland relatively rapidly, as hurricanes typically do, it parked itself or right off the coast of Houston, Galveston, Freeport, and stayed there for some almost 36 hours. And during that time, it was a very wet storm, so huge amounts of water fell. In portions of Houston, they received as much as 60 inches of rain. It was one of the largest rain events that's ever occurred. And very likely, it's a direct result of the increased water temperature and properties in the Gulf of Mexico that we've discussed. And as a consequence, huge areas of Houston were flooded, mass of people displaced, billions of dollars in damage occurred. And so that was a major catastrophe. However, the roots of the catastrophe had to do not just with the severity of Hurricane Harvey and the unprecedented large rainfall that it produced, but the way in which the urban plan of Houston had been laid out with respect to water management and water distribution. So a lot of the development in Houston, and probably many of you are not familiar with the geography of Houston, but Buffalo Bayou runs through the center of Houston. So Houston is here, the sort of downtown region of Houston is here. It sprawls in all directions, but I-10 is roughly sort of in the northern portion of the city. And these reservoirs, this is not to scale, but these reservoirs represent impoundments of water that collect water that would otherwise be distributed across large areas of the urban landscape of what is present-day Houston. So Houston is sort of naturally a large area of seasonal wetlands, but by building these dams, those seasonal inundations are controlled and managed. And so the Addicks Reservoir and the Baker Reservoir, these are impoundment systems, flood and dam management systems that were added, starting in the late 1970s and added on to continually. And then all around these areas, they allowed the urban planning of Houston allowed for the development of urban housing. And so, the concept is that you have these dams, these waters that fill up, and under normal time, the water goes out the drain. So, typically in this system, you have water being added from upstream flow or from rainfall, and this water is discharged and out the Buffalo Bayou system, and eventually it makes it to the river and flows out into Galveston Bay. So that's the normal system. And then by impounding it in these areas, the surrounding regions are available for urban development. So that's the concept. So the reservoir works by impounding this water. It releases water through these drainage systems to maintain that bank fill limit. However, if the drain can't keep up with the supply, then the water flows over and out of the reservoir, or the bathtub in this diagram. Well, so what's the problem? The problem is that, for example, with this Adix reservoir, the one in the north of the diagram that I just showed you, urban planning was such that they allowed housing development right up into the area that would overflow if the dam filled up. So when Hurricane Harvey happened, the bank fill limits, in other words, the limits of the potential impoundment area created by the damming of this reservoir, was high enough to actually flood large areas of the surrounding urban development. And that's what you're seeing here. So the Adix reservoir is the impoundment system is up here, and the water has fallen and filled up this reservoir so deeply that adjacent houses are being flooded. Well, so that was one problem. And then in order to try to control that, they released water over the dam and flooded housing on the outside of the dam structure. So, you can imagine that the urban planners that did this, to some degree or another, would not have anticipated a storm event as massive as what Hurricane Harvey produced. Nonetheless, allowing urban structures to be, urban development and housing developments to be situated within the potential dam and high water limits of the reservoir is sort of courting disaster. And that sort of, it's a sort of a disaster that occurs, very rarely, once a century. This is sort of a 100-year flood event. Well, the 100-year flood events are becoming more and more common, and that sort of metric really doesn't apply very much. And so that's a factor. All right, so urban management of water is a critical component in how we understand water management. What about water management for wetlands? Well, wetlands are critical habitat for water management. These are natural systems. They're located in mostly areas of low relief, flat regions where land and water are both present at the same time. Typically, you get marshes, bogs, swamps, and these areas, these wetland areas, are critical for biogeochemical cycles, for natural systems. And if you think back to the passage of the Clean Water Act and some of the major environmental legislations, one of the things that that legislation and that management was concerned with doing, one of the principal things, was preserving wetland areas for both in terms of their natural habitat for natural ecosystems, but also because they facilitate a more informed and sustainable means of water management. Characteristics of wetlands is that they typically have poor drainage, there's low dissolved oxygen present in the water and the soils, and there's this, typically specially adapted vegetation. What does wetlands do? Wetlands buffer the overflow, they mitigate flooding, they allow for groundwater recharge, they filter polluted waters, they're critical habitats for fish, birds, shrimp, etc. And they buffer zones in coastal regions against flooding. So one of the things that they did in Houston was to dam up areas and stop the flow, the natural supply of water into areas that would have been seasonal wetlands, and impound that water in dams and reservoirs. and then transform that previous wetland area into housing developments and urban habitat. And so poor wetland management was very much at the heart of the flooding caused by Hurricane Harvey. And it's something that we see in water management areas and flooding typically in many other areas. There were floods last year, 2019, that were caused by the failure of dams. And so high amounts of water, dams that were built in the 1950s or even earlier, poorly maintained. The failure of these dams and reservoir systems produces then flooding downstream. And so this maintenance of these water management structures and the desire to maintain natural systems are very much at the heart of water management policy. Okay, so now, up until now, we've been talking about water, excess water. What happens when we have too much water? How do we manage water and to preserve wetland ecosystems and so forth? But earlier in the lecture, we talked about ideas of drought and what happens with drought. Well, I want to switch gears now and turn the clock back to 2017 and look at a situation which arose due to drought, not in the United States, but in the what's called the dry corridor of Central America. So I'm going to now play a video which should give us sort of a flashback.
You got some bad people in those groups. You got some tough people in those groups. And I'll tell you what, this country doesn't want them.
The caravan is an epic story of human migration. And it's a phenomenon that stirs different reactions in different people.
They are being portrayed as criminals, which they are not. They are within their rights to come here and seek asylum.
For me, the caravan raises a question related to a recent trip I made to Central America, to an area called the Dry Corridor, where I witnessed the impacts of a severe drought that's linked to climate change and has devastated agriculture.
Ya no va a perder. Todo está perdido. Está perdido. Todo eso está perdido.
This year, in just one dry corridor country, Honduras, 80% of the corn and bean crops were lost.
The dry corridor of Central America is particularly vulnerable to this issue of climate change and its impact on food security.
The food insecurity is so dire that 2 million people are now facing hunger. I also learned that the drought has been made worse by El Niño, the warm water off the coast south of Central America. We're currently in an El Niño year, and the future looks even scarier. Scientists believe El Niños are becoming more frequent with a changing climate.
Experts say what's known as the dry corridor in Guatemala has grown 25 to 30% in the last decade.
So now, my caravan question is, have some of these migrants left their homes because of climate change, drought, and hunger?
Fue en esta ciudad del noreste de Honduras, San Pedro Sula.
This caravan idea first sparked in October in Honduras, in the city of San Pedro Sula. People from all over the country rushed to join after hearing on TV, radio, Facebook, and WhatsApp that they would no longer have to rely on smugglers. A caravan was being organized, a relatively safe and virtually free way to get to the United States. I'm catching up with the caravan once they've already been on the road for a month, traveled almost 1,000 miles, and are arriving in Mexico City. I find a lot of people who worked on farms and say that they fled because of the drought.
Mira, hubo mucha sequía. Hubo mucha sequía, las milpas, la mazorquita es pequeña.
Among the farm workers who joined the caravan in Honduras was Pedro Castillo.
Siempre cuando sembramos vamos buscando tener la comida, arroz y frijol y maíz. Y hay mucha gente, así sobrevivimos. Hay mucha gente que sobrevivimos con menos de $1 a veces al día.
Perdón, pero con respeto le voy a preguntar eso. Me parece que es una vida de un pobre. ¿Así es?
La verdadera realidad de los hondureños. Estamos asumidos a la pobreza y no porque seamos haraganes. A veces, bueno, digamos que con la madre naturaleza no se puede hacer nada. Cuando viene la sequía no se puede hacer nada.
Perhaps the one thing you can do is flee. That's what Fabiola Diaz and Carlos Salinas are doing. They and their kids are traveling together, even though they didn't know each other before. They're not a couple, but they seem like a family. Fabiola and her 2-year-old son Yeltsin come from a Honduran town called Santa Barbara. ¿Qué son los tipos de trabajo que hacen?
This is not innovation. This is a drop in the bucket of what comes to the border every month, every week.
Atenas Barola is an attorney from North Carolina who's part of a group that's come to Mexico to advise the migrants on U.S. asylum law.
I'm following the story of a young woman who is fleeing because of poverty and hunger. She's living on a meal a day. Does she qualify for asylum if that's the only reason that she's fleeing?
That is the only reason that she's fleeing. Unfortunately, in the United States, she is not going to qualify for asylum.
Is she not fleeing for her life? Is she not possibly in danger of her life if she doesn't get food?
She probably is, but the way that the U.S. asylum law is written is that it is for people who are fleeing persecution, not economic asylum.
Even with American asylum a virtual impossibility for climate migrants like Fabiola and Carlos, they are nonetheless pushing forward on their journey to the United States. And to help them on their way, the Mexico City authorities are shutting down the subway system early on a Saturday morning and giving it over to the caravan so it can traverse the city and continue its trek northward. When Carlos joined the caravan, he decided to leave his wife and 2 kids at home and bring his 11-year-old daughter, Angie.
La Fabiola y Yeltsin son amigos.
Sí,
¿Y qué piensas de ellos?
ve que ella cuando trae su niño, se cansa con el coche, trae bastantes cosas. No hay nadie que la ayude con eso.
¿Usted está ayudando?
Sí,
Tuve que acabar la escuela. Eso era difícil. Fue difícil, pero uno en veces por tomar una decisión y por tal vez por salir adelante. Tomé la decisión, la saqué de la escuela y me vine. No sé. Ya estamos aquí ya y vamos a ver si cruzamos a la playa.
To cross over, they still need to reach the US border. And for the last 1,000 miles of their journey, they walk, they hitchhike en masse. And some amazingly catch buses chartered by Mexican states to take them all the way to the border city of Tijuana. This is how Tijuana greets the caravan. It's a far cry from the warm Mexico City welcome. And while the total number of caravan migrants may not be overwhelming, the city's anti-caravan mayor nonetheless calls the influx an avalanche and a tsunami.
Buenos días, Fabiola. Habla Juan Carlos Frey, periodista de Estados Unidos. ¿Cómo estás?
I left the caravan for a few days, and now I'm heading back, trying to reconnect with Fabiola and Carlos. I hear that Tijuana is housing the caravan in a community sports center that sits literally on the border with the United States. So I head there to find them. And here she is.
están? ¿Qué van a hacer?
Esperar y
¿Sabes qué tan cerca se está?
If they just cross the wall, they are so close to their American dream, but have no idea how to finally reach it.
The United States will not be a migrant camp, and it will not be a refugee holding facility. It won't be.
In fact, crossing over seems more impossible than ever.
We're facing a man-made disaster of global scale.
But if you ask the climate migrants who lived through the severe drought and the hunger that followed, they'll say that joining the caravan was something they simply had to do.
Yo siempre he pasado la pobreza, pero jamás he querido abandonar mi tierra porque tienes tus hijos, tus papás, tienes tu familia. No, yo creo que no hay un lugar donde te sientas más cómodo que en tu tierra. Pero igual cuando ya sientes el hambre ya te trae encima y tal vez tus hijos te están exigiendo, papá, quiero comer de tal cosa, quiero comer comida buena, quiero comer carne. Entonces es ahí donde te llenas de coraje y dices, me voy.
All right, so that was a look back to a few years ago when it really became clear that not only were there mass movements of people created by climate disasters and specifically drought issues, but that those mass movements directly affected politics and society in the United States. And so that situation, although circumstances have changed and we have different crises, is still at the bedrock of how we consider the impacts of climate on our system. And so in the lecture that I'll be giving on Thursday, we'll look at drought as a driver of immigration and political strife. We'll define drought. And then we'll look at how drought is managed and temporarily correlated. We'll look at some metrics of how drought is used, and then we'll consider drought as a local and statewide problem. But I'd like to conclude my lecture for the moment and stop sharing my screen. And I'd like to address the fact that today is the election day, and we are all in the process of voting and making a decision about what sort of policies we're going to have in the months and years and decades to come. And I feel like we can't just sort of let this occasion pass without having some discussion. So first of all, I'd like to ask if everybody would, with a show of hands, indicate whether or not you have voted. So, if you voted or plan to vote today, please raise your hand. I'd just like to look down and see what's going on. See, look at that. Well, that's great. And if you haven't voted yet, do you have a plan to vote, and are you able to do so? Looks like we have pretty widespread agreement that this is an important factor. I wonder if I can just open this up for discussion. When you think about the choices that you make for voting, and first of all, the choice to vote, and then which of the candidates you're going to choose, how much, and this is a sort of a subjective question, of course, but how much do issues of the environment, of climate change, factor into your decision making? And I'd like to hear some comments and some discussion about that. So does anybody want to say whether their decision to vote or for whom they voted, how much that was affected by climate change and the kinds of environmental issues that we've discussed in this class? Anybody have any comments on that?
Well, I mean, as environmental scientists, I think it is selfish of us to vote for the environment too. Our careers depend on it, so I know probably a lot of us put in retrospect the climate crisis and what is going on.
Yeah. So you're saying that it's selfish to vote for the climate? I didn't quite.
Well, no, I meant like as us, like for us being, we have an
interest.
Yeah, an interest, right?
You got a dog in this fight.
Yeah.
Okay. Any thoughts on that? Any other comments on that?
I totally agree. I mean, I think a lot of us in this class are kind of nearing graduation, and if not, we need to plan for the next 4 years. And I think voting for whoever we believe will make the best decisions for, our longevity and success in our field and why we've spent this money on a higher education. I mean, this was my first election. I haven't been able to vote yet. And it was awful, but also, exciting, I guess. But I mean, we all have a voice, and we can at least try to change our career paths and make it the most easily accessible for ourselves in the future.
Anybody else want to comment on that?
No. Okay.
Well, let me pose another question. We're sort of at a crossroads. Not sort of at a crossroads. We are at a crossroads. We will either continue with one set of policies. We'll either rejoin the Paris Accords, or we'll leave it permanently. Apparently, we announced our intention to leave the Paris Accords for climate mitigation, but we haven't yet fully severed. So the final separation from the Paris Accords has not yet occurred. President Trump says that will be finalized if he's reelected, and Vice President Biden has said that one of the first things he would do, he says he'd do it on day one. He's got so many things he's going to do on day one that's going to be a really busy time. But that's what he says. He's going to rejoin the Paris Accords. What do you all think, having sat through my lectures and your discussions and your research, what do you think some of the most important decisions that we have to make, besides just rejoining the Accords or not rejoining the Accords? What are some changes or policy changes that that are important in the coming years?
I do think that as in your lectures, you do discuss like the environment as a system. So I do think that globally we need to be together against climate change, and we need to be working with other countries and stuff, especially since we all know that the US loves to separate ourselves. So I think that we do need to start looking at, climate regulation on a global scale, just as you say with the environment, that it is on a global scale. So I do agree that getting back or not leaving the Paris Accord would be great. And we all need to, I do think we need to start realizing, sustainability has this great economical value to it. We have to stop over exploiting resources and creating that tragedy that we constantly talk about.
Yeah, well, but let me put this to you. So, because of the pandemic, we are, and because the economic consequences of the pandemic, we find ourselves in our society in a state of disarray that is really unprecedented in my lifetime. Maybe December 8th, 1941, you know, after we've been bombed by the Japanese, that might have been, you know, a time of greater crises. I'm not sure, but certainly now, looking at, you know, hundreds of thousands of small businesses closed, you know, 20, 30 million people out of work, people's savings depleted, you know, the many of the industries that, you know, were the bedrock of our society, sort of threatened or uncertain. The airline industry, the energy industry, the hospitality industry, you know, all that sort of, you know, with a very, very uncertain future. You know, how can we think about, you know, climate change? How can we think about the environment? You know, shouldn't we, you know, can we think about this as an opportunity or as a challenge or something that needs to be put aside until we deal, you know, with more pressing issues? So how would you all prioritize, you know, environmental policy changes or climate policy changes in terms of the pandemic and the economic crisis?
I kind of said this in the chat, but I think that it's hard to kind of prioritize certain issues over other ones, but climate change focuses on like a couple other issues as well, because when you factor in like environmental racism and like other issues like that, tackling climate change is also tackling environmental racism, because people of color are at like the brutal front of climate change as we speak. Like they're the ones that are being impacted the most right now. And so fixing and like working on combating climate change is also like putting us one step further in environmental justice.
Mm-hmm. Mm-hmm. Well, as a historical matter, let me, I referred to the, you know, the beginning of World War II with the, you know, the bombing of Pearl Harbor and America's entry into World War II. And that was a moment, I think, that, you know, we acknowledged that this was a crisis, and we acknowledge also with some pride and satisfaction that the country rose to meet that crisis. And, you know, in 4 or 5 years of you know, tremendous sacrifice and sustained effort, they managed to defeat fascism and Nazis and Imperial Japan and transform the country and the world. So that was a success that came out of an initial crisis. But if you look into the sort of the changes that occurred, you know, World War II happened after the United States had been through a decade-long process or period of economic constriction, calamity, crisis. You know, the you know, economic system had more or less really collapsed and constricted starting in the 30s, going all the way through the decade of the 1930s. You know, there was mass unemployment, you know, high levels of poverty, childhood poverty. You know, so it was a really, really difficult time for Americans. And that difficult time and those possibilities were changed because of the massive investments that the federal government made to support the war effort. And you can, you know, you can document this historically. There's a wonderful book by Studs Terkel called The Good War. And he did interviews of people who lived through the war. This is written some, I don't know, 20 years ago, I guess, is when this book was written. But he went back and was able to interview living people and get their impressions. And again in his telling of that history, you find people in societies that had always struggled historically, had always been deprived and sort of at the edge of poverty and, you know, poor development, never had really gotten the benefits of society. And then came these massive government contracts, you know, massive influxes of investment. And, you know, after the war was finished, that level, that sort of raising of all the boats kind of continued. And, you know, that was really the seeds of, you know, the boom periods of the 1950s, 60s, and early 1970s. So is it possible that at this moment in crisis that we find ourselves, if we chose as a society to say, okay, we need to have a war on climate change, or a war as a sort of a poor metaphor for what we would have to do, because we're not trying to defeat a human enemy. We're trying to change our own nature, the nature of society. But that will require massive investments and massive transfers of the way in which we organize society. So, there is an opportunity, within how we decide to meet climate change, the challenge of climate change and other challenges that are at hand, that could potentially, despite the sort of sacrifices that we have to make, lead to a much better society in the future. And I wonder if, so that's my thesis. I wonder if people care to agree or disagree. And of course, we're at the end of the hour, so you may depart if you have other obligations. But I'd be interested to hear what you think of that thesis. Nobody thinks, nobody has any ideas. Am I completely off base? But so if that happens, if we are to transform our societies, supposing everything that I said is true, suppose we, invest in solar energy and wind energy, and transform from fossil fuel-based transportation system to transportation with electric vehicles or other sorts of technologies that maybe we haven't even thought of yet. If that happens, the population that is attending college now, that's you represent in this class, you are the people that are going to have to do that work and potentially gain the benefit from that. So I wonder what you think, looking forward to that sort of a future.
I think we would have to be completely unified for that to have a realistic shot of happening. And I don't know if that, the way we're going right now, I think that we're moving more apart than we are together. So as much as I'd like that, something like that to happen, I don't know. I just don't see it happening.
So you think that the sort of polarization, right and left political polarization that everybody thinks about, is a sort of a given, and has changed the landscape to where, there was tremendous polarization during Roosevelt's era. He was denounced as a socialist and widely reviled by more conservative political forces when he was president. But the attack of Pearl Harbor really united everybody, and in a overnight, literally overnight, everything changed. And I wonder, are we in are those circumstances the same? Could we look for some change like that, or are we too far gone down? So it seems like you're saying that we're just too polarized ever to come together for such a large purpose.
I have a comment real quick.
Yeah.
I know that right now things are very polarized, and I tend to be a very negative person. And I like to tell myself that, we only have to wait until we're 35. That's not that far away. I think change will come, and it will come in waves, and we're gonna have a two-party system probably for the foreseeable next 50 years, because things like these take an extremely long time to change. And I think it can be done, and I think sustainability would be a great motivator for people to come together. It's just a matter of making it a hot topic, making people want to invest in it, and making people want to take the step to work together. And you got me on that one. I don't know how to make that happen, but that's why we're all taking these classes and trying to do stuff, do outreach, and just get people educated, and hopefully they can make informed decisions just like they do when they vote.
Yeah. Well, how does the crisis of the pandemic, how does that inform, what does that indicate about how we might respond to the, as impactful as the pandemic has been, potentially climate change, at least locally, has the potential to be just as impactful or even more impactful. And I wonder how, when I look around and you know, like in Tallahassee, everybody seems to be cooperating to an extent. I mean, when I go to Publix or out and about, people are wearing masks, and you know, there is some sort of attempt to social distance. But then I look on the media and they say, oh, well, you know, the Montana and, you know, rallies for President Trump, you know, people are ignoring the mask mandate and, you know, denying that, you know, there is such a, you know, that the pandemic is as serious as, you know, scientists say it is. So I, you know, that's a, you know, I wonder what you all think of you know, how the pandemic indicates how we might respond as a nation to these large intractable challenges.
I guess I have a little comment on that. Is like talking with I was talking with one of my parents, like a parent the other day, and we were like, going back and forth about just how polarizing it is different in like cities, because I'm from like a huge city of Jacksonville. So trying to have these conversations with some, like a city that is so vastly different than ours, like especially because I have one parent at the beach and one in town. So I have like a beachside community, which is again, completely different from Leon County, because like a lot of people ask me why I don't vote here. And it's like, I don't care about as much, I don't care about as like the policies here as much as like the beaches policies. So I feel like living with through this COVID, I've seen that it's hard for us to, or it's hard for me to connect what like news outlets and scientists are saying with like our local community, like super quickly, because they just touch so much on like the broader cities, and it's too generic of like, oh, this is how it's happening in this community. But it's like, we're too, like we have such different communities everywhere that I guess it's hard for me to see any connection between like the science that they're giving us and me trying to like argue my way through COVID. Because being in Tallahassee, I personally have like, it's hard for me and my roommates, we've had these discussions of like, how much do we keep caring about like people going out anymore? Because like, we'll sit back and we'll be like, okay, should we just go to Madsko? Like we can sit outside. We can sit outside at the bar. And then it's like, no, we don't want to do that, because it's like, we want to respect the social distancing boundaries. But then it's like seeing how many students, especially at the party school of FSU, who go out and don't get sick, or who've been like exposed and therefore aren't sick. It's like hard to see it's a super big disconnect between scientists giving us facts and then us as like college students living with people going out. And I guess that's my opinion. So it's hard for me.
Yeah. Anybody else want to comment on that? I guess we're over time now, but as I say, I'll keep the discussion open until 2 o'clock. So if anybody wants to.
I think
that you're right, though. I think that people will continue to be in denial until something makes them stop being in denial, like a big event. Because the way it's going right now, where everything's going gradually and things keep happening like a little bit at a time, is not going to be enough to like make people like, you know, see what's happening.
Yeah, but the pandemic is not under control, is it? I mean, you know, it's you know, we sort of as a society in, you know, patchy response, but generally speaking, we didn't follow guidelines that might have, you know, flattened the curve and reduced the spread of the pandemic. And here we are with, you know, 100,000 people a day getting sick, getting infected. Now the death rate is down and we're better at treating it, but you know, that that's something which has not yet run its course. I mean, you know, it's astonishing to me, you know, to wonder. I don't see a clear end to this pandemic, particularly with winter coming on, and you know, such an incredible how widespread the virus is. In different communities, you know, both rural communities, and sort of nowhere is, you know, is safe. There's a reservoir of virus everywhere in every city, and you know, young people can probably get it, and most of them will be okay. But you know, there's this huge vulnerable portion of the population, something like 25% of people, either by age or pre-existing conditions, are you know, vulnerable to severe illness or even death from the COVID. So it's remarkable, and we haven't yet got our arms around it. And you know, and the solutions are, you know, it seems like the solutions to the pandemic, you know, as difficult as it is, as challenging as that is, at least we sort of know how to do it. We could control it, you know, with masks and social distance. We can develop better therapeutics. We can, you know, try to target resources where they're needed. So these are all things that we can do, and maybe we'll do them if there's a, you know, a change of leadership. But still, the problem is huge, but really, it's you know, the potential impact of climate change is so much larger. You know, it's kind of disheartening for me personally, if I can say that. Okay, well, I guess I'll say goodbye to everyone, and if you haven't voted, please go vote. And it'll be interesting to, when we get back together on Thursday, it'll be interesting to see if we know how the outcome is, or if we're still waiting for things to be decided. It's a very sort of suspenseful time, and in so many different levels. And hopefully we all keep an open mind and willing to listen to each other and get the ideas that we can. So I'll end the class for today. And remember, you have your milestone 3 coming up. Carrie will be putting out appointments for the teams to meet, and I'll look forward to talking to you later on. All right, goodbye, everybody.